Welcome to the Joy of Architecture.
Great to be here.
Today we are embarking on a really interesting deep dive. We've got some fantastic source material in front of us.
Yeah, it looks really comprehensive.
It really does. It takes a close look at two, well, titans of the programming world, Java and Go, or Golang as it's often called, and specifically through the lens of building API microservices, for those big, large-scale, cloud-native enterprise systems.
Right, that's a critical context these days.
Absolutely. So our mission really for this deep dive is to walk through this analysis together. We want to pull out the key insights, the core nuggets of knowledge.
And help you, the listener, understand the really crucial differences and, importantly, the trade-offs between Java and Go in this specific microservice world.
Exactly. We're not aiming to, crown a winner here. That wouldn't make sense.
No, definitely not. It's more about understanding the strengths, the weaknesses of each language based only on the analysis we have here.
So you can figure out which one might fit your technical needs, your operational realities.
Makes sense. So the material lays out a pretty detailed comparison, looking at everything from the core language design
Yeah, the philosophy behind them.
to performance, how they handle concurrency, which is huge for microservices, the whole ecosystem around them, libraries, frameworks.
And then the really practical stuff like DevOps, deployment, how easy they are to actually run.
That sounds like a solid plan.
Okay, let's do it. We'll start right at the beginning with those fundamental design philosophies. That really sets the stage, doesn't it?
It absolutely does. It's where you see the first major divergence, and it impacts almost everything else we'll talk about.
So the sources, they kick off contrasting Java and Go's core ideas. Java obviously has been around the block, decades old, deep roots in enterprise.
Oh, yeah. And its whole design is built around object-oriented programming, OOP. Classes, objects, inheritance, polymorphism.
All those concepts, groundbreaking stuff back then, and still super relevant for building complex structured systems today.
Definitely. And you really see that maturity reflected in how the sources describe it. It's stable, huge standard library, battle-tested over years and years.
And that ecosystem, it's just massive, isn't it? Third-party libraries for practically anything.
It really is. The sources also make a point about Java's strong, static type system.
Right, checking everything at compile time.
Exactly. Which helps catch errors early, makes applications more robust, more reliable. Really important for enterprise stuff.
And then there's the whole JVM aspect. Java compiles to bytecode.
For the Java virtual machine, the classic write once, run anywhere.
Though maybe write once, debug everywhere sometimes felt more accurate back in the day.
Maybe. But the JVM itself is sophisticated, right? It's not just running the code, it's doing things like just-in-time compilation. We'll get into that with performance.
Okay, so that's Java. Now, Go. It's a different beast, designed more recently.
Yeah, came out of Google. And it was really designed with modern problems in mind networking, concurrency, building big systems efficiently.
And the philosophy feels simpler, more minimalist.
That's the word that keeps coming up in the sources. Simplicity. Fewer keywords, cleaner syntax. Definitely leans more towards a procedural style. Less ceremony, maybe.
It favors composition over inheritance, right? That's a key difference.
Yes, definitely. And it uses implicit interfaces. So a type satisfies an interface just by having the right methods. No need to explicitly say implements.
Which can make things a bit more flexible, less coupled sometimes.
Potentially, yeah. It's a different way of thinking about structure.
What's the big design thing in Go that the sources say makes it great for microservices straight away?
Well, that has to be the built-in concurrency.
Yeah.
Go routines and channels.
Right, it's not just a library you add on.
No, it's baked into the core language. Inspired by CSP, communicating sequential processes. The whole point was to make concurrent programming easier, less error-prone than dealing with threads and locks directly.
And those compile times everyone talks about, that's part of the design too.
Absolutely. The sources mentioned that fast compilation is a huge productivity win. And critically for microservices, it compiles straight to a single static native binary.
Meaning no JVM required.
Exactly. No external runtime needed.
Yeah.
That massively simplifies deployment artifacts, the whole containerization story.
Okay, so two very different starting points. Java, mature, OOP, JVM-based, Go. Simpler, procedural-ish, native compiled, built-in concurrency. How does this affect developers day-to-day, like learning it, being productive?
Well, the sources suggest Java often presents a steeper initial learning curve. You've got OOP concepts, that vast ecosystem to navigate, understanding frameworks like Spring.
Yeah, it can feel like a lot if you're new to it.
For sure. But, and this is important, the sources also say for experienced Java devs, especially those who know Spring really well, productivity can be super high. Those frameworks handle so much complexity for you.
Right, it's an investment, but the payoff for big, complex stuff using standard patterns can be huge.
Precisely. Go, on the other hand, is generally seen as easier, faster to pick up.
Simpler syntax, smaller feature set.
Exactly. So developers can often get productive much faster. The sources point this out as a benefit for quicker onboarding, getting that initial velocity, especially for network services and APIs, which is what microservices often are.
Okay, let's talk about that classic debate. Verbosity versus clarity. The sources dig into this a bit. Java gets called verbose.
Often, yeah. All those explicit type declarations, public, private, protected everywhere, the class structures.
It can feel like a lot of boilerplate sometimes.
It can. But the flip side, as proponents argue in the sources, is that this explicitness provides structure. It makes the intent clear, almost like self-documentation.
Okay. But modern Java has things like var and records now, right? To cut down on some of that?
It does, yeah. Features like var for local variables, records for simple data carriers, and tools like Lombok definitely help reduce the boilerplate compared to older Java code.
And Go is usually praised for being concise, readable, especially with Go famping and forcing style.
True. But interestingly, the sources bring up what they term Go's potential vertical verbosity.
Vertical verbosity, what's that?
It's specifically about the error handling. That common pattern. If error, nil, return error.
Ah, you see that everywhere in Go code.
You do. Each line is simple, clear, but you repeat it a lot, which can make functions physically longer down the page compared to, say, Java's try-catch exception handling.
So Java might be horizontally verbose,
Right.
longer lines, more detail per line, but Go can be vertically verbose with more lines just for error checks.
That's the trade-off the sources highlight. And they correctly point out clarity is really subjective here.
Yeah, what one team finds clear, another might find noisy or repetitive.
Exactly. Depends on your background, your team's conventions, what you prioritize: explicit structure versus minimal syntax, explicit error checks versus exception flows.
This leads nicely into thinking about maintainability and just the feel of working with the language, the ergonomics. Java's tooling is famously mature.
Oh, absolutely. Decades of development there. The sources talk about the power of IDEs like IntelliJ, Eclipse, robust build tools like Maven, Gradle Bend, deep profiling tools like Visual VM, JFR.
That stuff really helps when you're dealing with big, complex systems.
Hugely. Plus, the established OOP patterns provide ways to structure complex code. The caution mentioned is that this richness can also lead to complexity itself. Dependency management headaches, navigating legacy code bases.
Right, the flip side of maturity, and Go's maintainability seems tied to its simplicity.
Largely, yes. The sources credit its simple syntax, clean structure enforced by GoFint, and those fast compile times as inherently good for maintaining code, especially for microservices that are meant to be small and focused.
And the built-in tooling helps too. Go test, go mug.
Yeah, that integrated tooling provides a consistent baseline workflow. The sources do note, though, that the lack of features like traditional inheritance or, until Go 1.0t, generics, sometimes meant more manual work or less elegant solutions for really complex data modeling compared to Java.
But generics are in Go now, which helps with some of that.
Correct. That addresses a key point for certain types of complex logic. But there's another really sharp insight in the sources about Go's minimalism. It's that the simplicity shifts more responsibility onto the development team for defining structure and patterns, without a super opinionated, all-encompassing framework like Spring.
Teams have more freedom, but also maybe less guidance.
Exactly. There's even a quote mentioned, finding an appropriate structure for a new project in Go can be quite tedious. Everyone structures their project differently.
Ah, interesting. So less built-in guardrails compared to Java with Spring.
That's the implication. Spring, with its conventions and weight, tends to enforce a certain way of doing things, promoting consistency across projects, even if it feels like more ceremony up front. Those are the guardrails the sources seem to be pointing at.
So Java frameworks offer a prescribed path, potentially better consistency in large orgs, maybe more boilerplate. Go offers language-level simplicity, more structural freedom, but consistency needs more team discipline or strong internal standards.
That sums it up well. It becomes a strategic choice. Do you want Framework enforced consistency and a vast feature set, or language simplicity and flexibility, knowing you might need more internal governance or custom pattern development.
Okay, let's shift gears from writing the code to how it actually runs. Performance, resource efficiency, these are absolutely critical for microservices at scale.
Paramount. And this is where the JVM versus native compilation really shows its differences.
Let's start with Java. Its performance story is tied to the JVM and just-in-time, or JIT, compilation.
Right. The JIT compiler is smart. It runs while your app is running, watches the code, figures out the hotspots, the bits executed most often.
And compiles those bits down to optimize native machine code on the fly.
Exactly. And it keeps doing it. It can optimize, de-optimize, re-optimize based on actual runtime behavior. The goal is maximum throughput over the long haul.
That's how Java apps can achieve really impressive peak performance, right, once they're warmed up.
Precisely. The JIT strength is adapting during execution. But the downside, as the sources stress, is that initial warm-up phase.
Before the JIT kicks in properly.
Yeah. The app might be running interpreted bytecode or less optimized code initially. For microservices, especially in the cloud, where things scale up and down a lot.
That warm-up delay impacts initial request speed and resource use during scaling.
Definitely. And then there's garbage collection, the GC, essential for managing memory automatically, but complex.
Oh boy, yeah. Always a fun topic.
Huh? The JVM has seen a whole zoo of GC algorithms over the years. Serial, parallel, CMS, G1, and newer ones like ZGC, Shenandoah.
Each with different trade-offs.
Right. Usually trading off overall application throughput versus pause times, how long the application has to stop while the GC cleans up memory. The sources really emphasize that getting top performance in Java often means deep GC tuning. It's an expert skill.
So powerful automatic memory management, but you need to know what you're doing to avoid performance hits, especially keeping latency low.
Exactly. Modern GCs like ZGC and Shenandoah aim for super low pauses, like sub-millisecond, even with huge memory heaps. But configuring them right is key.
And memory usage. Java apps tend to use more memory.
Typically, yes. The JVM itself takes memory plus object metadata, the JIT, the GC, and it adds up. That's why traditional Java microservices felt a bit heavy in containers.
Though the sources mention efforts to fix that. Quarkus, Micronaut, GraalVM.
Absolutely. The ecosystem is tackling this head-on, aiming to make Java much leaner for cloud-native deployment.
Okay, so how does Go stack up on performance? It's ahead of time compiled.
Totally different approach. AOT compilation means your Go code gets compiled directly to native machine code before you run it. A single executable file.
So no JVM startup, no interpretation, no JIT warm-up needed.
None of that, which is a primary reason Go apps typically start much, much faster than traditional JVM apps.
And the other big factor is Go routines, right? They're lightweight.
Incredibly lightweight compared to OS threads. The sources mention they start with tiny stacks, maybe 2 KB, and grow if needed. The Go runtime manages scheduling potentially millions of these onto a small pool of OS threads. Very efficient for concurrency.
And that efficiency helps keep memory usage down too.
Big time. AOT compilation plus efficient Go routines means Go apps generally have a lower memory footprint. Huge advantage for containers, serverless, allows higher density, potentially lower costs.
Okay, so Java, peak throughput via JIT, but warm-up and GC tuning needed. Go. Fast start, lower memory, efficient concurrency out of the box. How about that throughput versus latency debate the sources get into?
Yeah, that's a core trade-off. Java, once warmed up, can hit very high throughput, especially for stable, long-running workloads, thanks to continuous JIT optimization.
But latency can be spiky because of GC pauses?
Potentially, yes.
Yeah.
Even with modern GCs aiming for low pauses, it can be less predictable than Go's model without careful tuning, though things like Azul Ready Now try to pre-warm apps to reduce that initial latency hit.
In Go. More predictable latency.
Generally, yes. Fast startup, AOT code, and a GC specifically engineered for short, consistent pauses. The sources often quote under a millisecond contribute to low and predictable latency. Go also has strong throughput, especially for I/O-bound stuff where Go routines excel.
What about pure CPU-bound work?
The sources suggest that for really heavy, long-running computations, a highly tuned, JIT-compiled Java app might squeeze out more performance in some benchmarks, but it's not a given. Very workload dependent.
Let's zoom in on GC under load. That seems like a key difference.
It is. Under heavy load, especially high object allocation, Java's GC is working hard. The generational collectors are good at handling lots of short-lived objects, but tuning is critical to avoid long pauses or running out of memory. It's powerful automation, but complex.
And Go's GC. Simpler.
designed differently. It prioritizes low, predictable pauses. It's non-generational, which sounds less efficient, but its algorithms are tuned for that low latency goal. Plus, things like escape analysis and value types help reduce heat pressure in the first place.
Does it need less tuning then?
Generally, yes, according to the sources. Less knobs to fiddle with. But developers might need to be more conscious of allocations under extreme load and use techniques like sync, pool, to reuse memory manually sometimes.
Okay, maybe the starkest performance difference highlighted for cloud native is cold start time. Crucial for serverless, fast scaling.
Absolutely, night and day, traditionally. Java's JVM startup, class loading GIT warmup takes time. The sources give examples like 500, 600 milliseconds on AWS Lambda typically, even with optimizations like snap start, maybe 100 meters.
But this is where modern Java is fighting back hard.
Hugely. Grail VM native image compiles Java AOT, like Go. Project CRA lets you snapshot and restore a running JVM instantly. Both can bring Java cold starts down into the tens of milliseconds range.
So Java can be just as fast now with the right tech?
It can be competitive, yes, but it requires using these specific technologies.
Whereas Go's fast start is just how it works.
Pretty much. AOT compilation to a small static binary means minimal runtime overhead. The source is, quote, typical Go Lambda starts around 30-45 milliseconds. It's inherent. Makes it a natural fit for serverless and rapid scaling.
So the performance picture is really nuanced. Go shines out of the box for startup, memory, predictable latency, great for cloud density and elasticity. Java can match or exceed in peak throughput, and with modern tools like Grail VM Loom, is closing the gap fast on startup and memory, but often requires more tuning and specific tech choices.
That's a fair summary. The sources really drive home that the best choice hinges on your specific workload. Is it long-running throughput, millisecond startup, CPU versus I/O? Do you have JVM tuning experts or prefer Go's simpler operational profile?
That brings us perfectly to concurrency and parallelism, handling lots of requests at once. Another area with fundamentally different approaches.
Core requirement for microservices, absolutely.
Java's traditional way was OS threads, right? Platform threads.
Yep, one-to-one mapping with operating system threads. Powerful, but managing lots of them directly gets tricky. Synchronization, thread pools, avoiding deadlocks. It's complex.
And OS threads aren't cheap to create or switch between.
Exactly. That limits how many concurrent things you can easily do in one process.
Yeah.
Java did add things like fork join pool for better CPU parallelism, though.
But just like performance, there's a revolution here too. Project Loom.
Game changer. Loom introduces virtual threads. These are lightweight threads managed inside the JVM, not directly by the OS.
So like coroutines, they run on top of a smaller number of OS threads, MN mapping.
Precisely. The goal is massive scalability for I/O-bound tasks, but letting developers write code that looks simple and synchronous, like it's blocking.
So my code can wait for a database call, but it doesn't actually block an expensive OS thread.
That's the magic. When a virtual thread hits a blocking I/O operation, the JVM parks it, lets the OS thread run something else, and resumes the virtual thread later when the I/O is done.
And you can have millions of these.
Yeah, the sources say yes, potentially millions, with very little memory overhead per thread. It radically simplifies writing highly scalable I/O-bound code compared to the old async all that future hell. Loom also brings structured concurrency APIs to manage them cleanly.
Wow. Okay, that's a huge leap for Java in this microservice world. How does Go's model coroutines and channels compare now?
Well, Go was built with this stuff from day one. Coroutines, as we said, are incredibly lightweight, managed by the Go runtime scheduler, also MN thousands, millions, handled efficiently.
And channels are for communication between them.
Right, type-safe communication channels. Yeah. Sending or receiving usually blocks, which provides synchronization. It encourages that share memory by communicating style, passing messages around.
Which the sources suggest is maybe easier to reason about than shared memory and locks.
Often, yeah. It can make data flow and synchronization points more explicit, potentially reducing tricky bugs like race conditions.
So, thinking about the developer experience, writing concurrent code, how do they stack up?
Traditional Java concurrency, definitely challenging, according to the sources. Lots of pitfalls. Async frameworks helped but added complexity. Project Loom aims to make I/O concurrency much simpler with that synchronous style coding that scales.
And Go's model.
Widely praised in the sources for being relatively simple and intuitive. Coroutines are easy to start. Channels provide clear communication paths. The CSP model often feels more straightforward for newcomers to concurrency.
Okay, performance-wise, I/O-bound versus CPU-bound, how do the models perform?
For I/O-bound work waiting on networks, databases, traditional Java threads were inefficient. Project Loom's virtual threads are designed for this, making Java extremely competitive, potentially even better than Go in some scenarios due to other JVM optimizations, while keeping the code simple.
In Go.
Go's coroutines and runtime I/O integration are inherently great for I/O-bound tasks. That's always been a core strength.
What about tasks that hammer the CPU?
For pure CPU parallelism, Java has mature tools like fork join pool, parallel streams, and the JIT can really optimize that kind of code over time. Virtual threads aren't the tool for CPU-bound work, though.
And Go for CPU-bound.
Go can use all cores via GeoMax ProCS, and its compiled code is efficient. The sources sometimes hint that for very specific, long-running, heavy CPU tasks, a fully warmed-up, GIT-optimized Java might edge it out, but again, highly dependent on the workload and tuning.
So summing up concurrency, Loom massively boosts Java's I/O scalability and simplifies coding, bringing it very close to Go's inherent strengths there. Go's model is foundational, perhaps simpler initially. For CPU tasks, both are strong. Java may be having an edge in some highly tuned cases. Both are very capable now, just different paths.
Well put. The gap is definitely narrowed for I/O-bound workloads.
All right, let's zoom out again. The ecosystem. Yeah. Libraries, frameworks, tooling. This is huge for getting things done.
Absolutely critical. How much wheel do you need to reinvent?
Java's ecosystem. The word is usually mature or vast.
Unparalleled, really. Decades of enterprise use mean a gigantic standard library and an even bigger third-party world. Stability, battle-tested solutions for almost anything.
And for microservices specifically, the sources call out key frameworks. Spring Boot.
The dominant force, arguably. Simplifies building Spring apps, embedded servers, auto-configuration. And Spring Cloud adds distributed systems patterns discovery, circuit breakers like Resilience 4J.
Though traditional Spring Boot could be heavy.
It could, but newer versions plus Grail VMCRC integration are addressing that speed and memory issue.
Then there are the newer frameworks built for cloud-native speed. Quarkus, Micronaut.
Exactly. Quarkus Kubernetes native Java, heavily optimized for fast startup, low memory, often using build time magic and Grail VM.
Micronaut is similar, focused on modularity, testability, fast startup via compile time DI and AOT, avoiding reflection.
Plus all the mature Java tooling we mentioned.
Right. Powerful IDEs, build systems, profilers, big productivity boosters.
How does Go's ecosystem compare? Younger, leaner. Definitely younger, not as broad, but strong where it counts for microservices. The standard library is a major plus, especially for networking. HTTP2, JSON, crypto are built in and excellent.
So you might not need as many external libraries for basic stuff.
Often, yes. And the built-in tooling Go FMT, Go Test, Go Mod provides a solid, simple foundation.
But there are third-party web frameworks.
Oh, yes. Often more minimalist, though. Sources mention Gingonic, Echo, known for high performance, routing, middleware. Also, the Gorilla toolkit for modular components like its router.
How does this ecosystem difference impact productivity for building microservices?
It's a key trade-off. With Java and Spring, you get tons of pre-built components for complex enterprise needs, security, specific integrations, etc. Once you know Spring, you can build complex apps relatively quickly by assembling these parts.
In Go's productivity comes more from
language simplicity and the standard library for core tasks. Building simpler APIs can be very fast. But for more niche or complex enterprise features, you might be writing more custom code or integrating multiple smaller libraries yourself compared to pulling in a big Spring module. It's more like assembling building blocks versus configuring integrated components.
What about crucial things like observability, resilience, distributed patterns?
Java frameworks, especially Spring Boot Cloud, offer a lot here, often built in or easily integrated. Micrometer for metrics, Zipkin-Jaeger tracing integrations, Resilience 4J for circuit breaking, service discovery. It's often quite comprehensive and configurable.
And Go.
The standard library and concurrency model give you good building blocks for resilience. But implementing full-stack observability or advanced distributed patterns often means pulling in third-party libraries and wiring them together. Toolkits like GoKit help structure this, but the sources suggest the ecosystem for off-the-shelf integrated solutions isn't quite as mature or cohesive as the Java Spring world yet.
So, Java's ecosystem excels in breadth for complex enterprise needs. Go's is leaner, simpler, great for core microservice patterns using the standard library, but might need more custom work for advanced stuff.
That captures the essence of the comparison well. It depends on how much you need beyond basic API handling and whether you prefer a big integrated framework or assembling smaller pieces.
Okay, let's talk deployment, putting these things into production. DevOps. This seems like a major differentiator.
Huge difference, especially in cloud-native contexts where Go often shines out of the box.
Traditional Java deployment had JVM overhead issues.
Yes, the JVM adds size. Container images get bigger base OS plus JVM, maybe 300 middlebeat plus before your app, the sources mentioned. This impacts storage, network transfer, CI/CD speed.
There are ways to shrink Java images, though, right?
Oh yeah, multi-stage builds, Alpine, Distroless images, OpenJ9 JVM, AppCDS, lots of optimization tricks. But the JVM fundamentally adds bulk compared to a Go binary.
And startup time impacts DevOps, too.
Absolutely. Longer Java startup, JVM init, class loading, JIT warmup, slows down scaling, makes deployments take longer. Again, a GraalVM native image and CRAC are the big answers here, bringing startup down dramatically.
And the JVM just uses more resources running?
Generally, yes. Memory and CPU overhead. If not tuned well, it can significantly increase cloud costs, maybe 30–50% more, according to some points in the sources, compared to more efficient runtimes. That matters when you have hundreds of instances.
Go seems almost designed to avoid these issues.
Pretty much. That single static binary is key. No external runtime dependency. Just the executable, massively simplifies deployment.
Which means tiny container images.
Exceptionally small. You can use a cratch image, basically empty, or tiny Alpine, plus your Go binary, often just tens of megabytes. Great for CI/CD speed, storage, pull times.
And the fast startup we talked about is a DevOps win, too.
Huge win. Millisecond startups mean instances are ready almost instantly. Perfect for elastic scaling, fast rollouts, responsive serverless.
So comparing cloud-native readiness,
Go looks inherently cloud-native, the sources suggest. Small binaries, fast start, low memory. It just fits containers, Kubernetes density, serverless perfectly with little fuss.
and Java needs more work to get there.
It can be highly cloud-native, very competitive now, but it requires using those specific tools and frameworks. Quarkus, Micronaut, GraalVM, CRA. It's an extra optimization step compared to Go's default nature.
Image size and CI/CD speed seem like Go's advantage out of the gate.
Generally, yes. Smaller images mean faster pipelines, simpler deployment, just copy the binary. Java's larger images slow things down, and managing JVM versions configs adds a layer of complexity, though containers help standardize that.
How about configuring the runtime? Java has tons of JVM flags.
Incredible tunability. Memory, GC, threads. Powerful but complex, needs expertise. External config via FileSem bars is standard and well supported by frameworks like Spring Boot.
And Go's runtime configuration.
Much simpler, fewer knobs, mainly GOGC for GC tuning. Config via MVVars, flags, files is common. It leans towards sensible defaults over deep tunability, which can be simpler operationally, especially in dynamic cloud environments.
So overall, Go's static binaries give it a kind of natural DevOps advantage in the cloud, faster cycles, efficient resources, simpler ops. Java can match the efficiency with modern tech, but it takes more deliberate effort and tuning expertise.
That's the picture painted by the sources. Go's simplicity translates well to modern operational practices.
Okay, last big area. Scalability and reliability, pulling together everything we've discussed.
Right, how do they behave when you really push them?
Java scales horizontally, multiple instances.
Standard approach, yeah. And the JIT helps long-running instances perform well under sustained load. But the higher memory footprint means scaling out uses more resources overall, potentially higher costs.
And reliability under load. Any potential issues?
The main one highlighted is GC pauses. Untuned GC under heavy or bursty load can cause latency spikes, impacting perceived reliability. The sources also hint at the operational complexity of managing and tuning potentially hundreds of distinct JVM instances consistently.
How does Go compare for scaling and reliability, based on our earlier points?
Well, it also scales horizontally, but the lower memory footprint allows higher density, potentially lower cost scaling. The fast startup means new instances come online quickly during scaling events or failures, which boosts reliability.
And the concurrency in GC help too.
Definitely. Efficient coroutines handle high connection loads well, and the predictable low-pause GC contributes to more stable latency under load compared to untuned Java. That predictability is great for reliability in meeting SLAs.
So both scale, but Go might be more resource efficient and predictable out of the box at scale, while Java needs more careful tuning for consistency, especially GC.
That seems to be the gist. Though the sources rightly caution that bad architecture chatty services distributed monoliths will kill scalability regardless of the language.
This has been a fascinating deep dive. It really highlights that Java and Go are both incredibly capable for microservices, but they come at it from such different angles.
Exactly, and neither is standing still. Java's got Loon, Grail VM, CRAC, fundamentally changing its cloud-native story. Go keeps evolving with things like generics maturing its capabilities.
So the right choice. It's not simple. It depends entirely on your project, your team, your operational setup, your priorities.
Absolutely. Is it peak throughput you need most?
Yeah.
Or millisecond startup, the biggest ecosystem, the simplest concurrency model, operational ease?
Which leads to that final provocative thought. Based on this analysis, which set of trade-offs makes the most sense for you and your specific microservice needs right now? And how might that change as both languages continue to evolve?
A crucial question for any architect or team lead considering these technologies.
Well, hopefully this deep dive into the source material has given you a much clearer framework for thinking through those trade-offs. Thanks so much for joining us for this exploration of Java versus Go.
Yeah, we covered a lot: design philosophies, performance nuances like cold starts, the different concurrency models, ecosystem strengths, and the huge impact on DevOps and scaling.
Remember, the best choice is contextual. There's no single answer, as these sources make very clear. We hope this helps you navigate that decision. Please subscribe to Joy of Architecture for more deep dives like this one.